Okay, we are again with practice paper 2, and the marks will be given for the practice paper 2 as explained here. The way I am going to give you the marks for the practice paper 2 is same as the way I gave you the marks for the practice paper 1. 25 MCQs into 4, you get 100 for MCQ paper part. 2 structured essays into 30, 60 for structured essay. 1 essay into 40, you get 40 marks for the essay. Then total marks for the paper will be 100, 200. Then you can divide that by 2, you can get the final mark. Question number 1 is about quantum numbers. You know there are 4 quantum numbers: principal, azimuthal, or we can say angular momentum quantum number, magnetic and spin quantum number. Why we use these quantum numbers? We use quantum numbers to give the exact position of electron in an atom. But there are some conditions. When you write the quantum numbers, we have some rules. The question is this: the correct set of 4 quantum numbers for the valence electron of rubidium. Since rubidium atomic number is 37, you can go with the electron configuration of rubidium. It's 37. Then the configuration, if you write it from the beginning, this is how we get it. 3s2, 3p6. After 3p6, you know it's 4s2. After 4s2, it will be 3d10. After 3d10, it will be 4p. But up to this point, how many electrons? 4, 6, 10, 18, 20 and 30. We have 37. So then we need 6 more from p. It's 4p6. After 4p6, that will be 5s1. That's the configuration of the last sub-energy level. It's 5s1. The question is about the valence electron of rubidium. Valence electron means simply the last electron. Last electron is found in 5s1. So what could be the principal quantum number? Principal quantum number gives the main energy level. It's 5th main energy level. What will be the angular momentum quantum number, or in other words azimuthal quantum number? It gives the sub energy level. Sub energy level here is S means L should be 0. If L is 0, definitely ML should be 0. MS can be plus half O minus half. Plus half O minus half. Both are possible. So that answer is given in 5th one. So 5th one should be the correct answer. Second question is about rate of diffusion of a gas is. So first of all, we need the clear understanding about this word diffusion. So what's diffusion? Spread in gas due to concentration difference of the gas. As example, assume you then have used in a perfume. In that case, the atmosphere around you that has then high concentration of your perfume, right? But when you go away from you, what happened to the concentration of the perfume? It decreases. So one place you have high concentration, in the other place you have low concentration of the gas. Because of this concentration gradient, the gas molecules in high concentration area will spread into into the other area with low concentration. So that phenomena is known as the diffusion. Normally this diffusion of a gas depends on several factors. One thing is concentration gradient. So if there is a large concentration gradient, definitely the gas particle move fast. The other thing is the temperature. When you have high temperature, then kinetic energy of gas molecule is quite high, therefore they can move fast. That's the other factor we can have. Other than that, there will be another factor, it's about the molar mass. If the gas particle, heavy, what will be the rate of this diffusion? Rate will be then small. Heavy particle cannot move fast, it moves slow compared to light particle. Therefore, one thing is here, the rate of diffusion inversely proportional to the molar mass, because molar mass increases mean the particle becomes heavy. When the particle is heavy, I told you, it moves then very slowly. So because of that, these are the factors we have. You know, there is another word that's called effusion. This is diffusion, but there is another word, effusion. Escape of gas molecules through a tiny hole. As example, if you consider gas molecules like this, let's say this is where we have a gas. This is the gas molecules we have. That's confined in this area by a piston. So if you get small hole here, these gas molecules now escape through this hole. That process is called effusion. So then the factors affecting effusion also quite similar to the factors affecting diffusion. I told you diffusion is something else. Diffusion is something else. As example, assume you get a vessel A and vessel B, but vessel A is fully occupied by gases. Now initially the tap is closed. Once you open the tap, what happened? This area you have high concentration of gas particle, here low concentration. Now what happened? This gas molecule will then spread here to B. So after some time you see the gas molecules in B bulb increases. So that process is called then diffusion. High concentration area to low concentration area, diffusion. Effusion is simply escape of gas molecule through a tiny hole. So effusion or diffusion, both of these two have then same factors. There is a law called Graham's law, that's for effusion. It says that rate of effusion is inversely proportional to square root of molar mass. Rate of effusion inversely proportional to the square root of molar mass if the other factors remain constant. It's rate of effusion, right? But question is regarding rate of diffusion, but we can just apply this one for diffusion also. Not 100% correct, but generally we can say the factors affecting effusion, diffusion are the same. According to that, you know, directly proportional to its density? No, we don't have that type of situation. Directly proportional to its molar mass? No, it should be inversely. Directly proportional to the square root of its molar mass? Not directly. Inversely proportional to the square root of, yes, that's the correct answer for this one. That's the most appropriate answer for this question. So question number 2, answer is 4. Question number 3 is about N2O5. You know, that's oxide of nitrogen. We discussed 5 oxides of nitrogen mainly, N2O, NO, N2O3, NO2 and N2O5. This is the oxide which has highest oxidation number of nitrogen. We know this oxide exists as white crystalline solid. Other gases, some of them are liquid, some of them are gases. It is anhydride of nitric. Yes, when two nitric molecule combine and remove water molecule. Anhydride mean without water. Understand? When two nitric molecule combine and remove water molecule, what we get is N2O5. So therefore N2O5 is the anhydride of nitric acid. That's true statement. Question is about not true. It's not true, right? Second, in solid state it exists as NO2 plus and NO3 minus. Yes, I told you it's white crystalline substance, solid. In the case of solid, what we get nitronium ion. NO2 plus mean nitronium ion and nitrate ion. That's how we have this N2O5 in solid state. It is structurally similar to P2O5. Let's first go for the structure of P2O5. Actually, P2O5, the structure is something like this. You know, 2 phosphorus atoms are there. These 2 phosphorus atoms share 3 oxygen like this. You get single covalent bond like this. You know, oxygen valency 2, that's okay. But here then there is another oxygen atom in this side, another oxygen atom in this side. But the bond between these two, you can say it's a double, but actually in this particular case what happened, we call it P5D5 back bonding. P5D5 back bonding. What's the meaning of this? There is formation of pi bond. In that case, there is overlapping between p orbital of oxygen and d orbital of phosphorus. Therefore, the correct way to represent this bond is something like this. It's a coordinate bond actually between phosphorus and oxygen atom. So that's the structure of P2O5. But you learn the structure of N2O5. Is that similar to this one? If you remember it, N2O5 is something like this. We get two central atom, N2O5. So you get double bond oxygen on H nitrogen. There is a dative covalent bond between nitrogen and another oxygen atom. You know, there is one more oxygen, we place that in between these two atoms. So according to that, we get the structure of N2O5 like this. Are they similar? No, those are different structures. So the question is not true about N2O5. So third statement then false. So that is the answer for this. Its structure contain dative bond. Yes, this is dative bond. It can be prepared by heating HNO3 over P2O5. Yes, remember P2O5 is a dehydrating agent. Dehydrating agent means removing water molecule. Therefore, when you get nitric, 2 molecule of nitric, the water molecule can be removed by using dehydrating agent such as P2O5. So in that particular case, yes, N2O5 is formed in that case. We have several dehydrating agents. Concentrated sulfuric is a dehydrating agent. P2O5 is a dehydrating agent. Calcium chloride is a dehydrating agent. So likewise, we have several dehydrating agents. So P2O5 is a dehydrating agent. So it can remove water molecule from 2 nitric molecules. So what we get is N2O5. So that's true statement. So correct answer for this one is third one. Question number 4. An experiment is done to determine the relative molecular mass. 0.2 cubic centimeter of a liquid. You have a liquid sample here. It's liquid sample. The volume of this one is given 0.2 cubic centimeter. And the density of this liquid also given. It's 1.50 grams per cubic centimeter. That's density. Is vaporized. The volume is this. Okay, this is converted into the gaseous state. Vaporized means now we have gas. Here liquid state, here gaseous state. So once you vaporize this to gas, the volume becomes 56.3 cubic centimeter at STP, standard temperature and pressure at STP. Question is this, the relative molecular mass of the liquid is. Right, standard temperature. Remember in gaseous state of matter, the standard temperature is 0 degrees Celsius. Standard pressure, we know wherever you find standard pressure, it's 180 A. Right, now your question is to find out the relative molecular mass of the liquid. But you know, in liquid and gaseous state, we get the same component, same substance. Therefore, if you find out the molar mass or relative molecular mass of the gaseous state, so that is the relative molecular mass of liquid state substance, because we get the same substance. Okay, then how do we get it? You know, during this process, nothing happens on mass of this substance. Mass remains constant, because this sample is heated to get this sample. This water sample, then now this liquid sample is now the gaseous sample. Therefore, in both cases, mass should be then constant. But can I get mass from volume and density? Yes, all of you know mass equals density into volume. So that's the mass of this. So we have mass, you have volume, you have temperature and pressure of the vapor. Then to vapor or gaseous state, to gaseous state, you can apply now PV equals nRT. PV equals nRT. But we need to introduce then molar mass. Then PV equals mass over molar mass RT. You know, pressure is known, volume is known for the gaseous state, mass is known, it's same as this, R constant, T also known. Then you can find out the molar mass. So if I subject molar mass, what do we get? Molar mass is equal to MRT divided by PV. MRT divided by PV. This is derived equation for the molar mass finally. But the mass of this one can be replaced by density and volume. You know, M equals dV, dV RT over PV. But what about this V? It is the volume of the liquid. I take it like V dash, V dash. So this will be V dash. So we have everything except molar mass. So you can find out molar mass by substituting the values. But I don't have space here, so I write it here. Then molar mass of the liquid is equal to density. It's 1.50 grams per cubic centimeter. Volume of the liquid 0.2 cubic centimeter. Then R is universal gas constant. You can keep it in SI unit. It here 8.314 joules per moles per Kelvin. And finally temperature. You know, temperature I told you, standard temperature it's 0 Celsius. In Kelvin it should be 273 Kelvin divided by PV. So what could be the pressure here? It's 1 atm. Since I got the SI unit here, it should be in Pascal. So you know 1 atm means 110 to the power of 5 Pascal into volume. What about the volume of the, this is volume of the gas. It's 56.3 into, you know, it should be in cubic meter. Cubic centimeter to cubic meter 10 to the power of minus 6. So that's the correct substitution. So all the units will be cancelled out. Finally you get molar mass in grams per mole. Grams per mole. It should be 119.4. If you simplify this, it's this one. So that's a molar mass, 119.4. Then when you remove this unit, that will be the relative molecular mass of the liquid. Question number 5 from gaseous state of matter. The density of carbon dioxide will be highest. I think in the previous paper I told you, we need to memorize then some derived equations like PV equals nRT. We have some derived equations, so we have to remember these things. I think you remember this equation, D equals Pm over RT. That's the equation for density of an ideal gas. So if you assume carbon dioxide here ideal, this will give then density of carbon dioxide. But you know R constant, capital M constant. Molar mass of this one is constant. But the question is now, density of carbon dioxide will be highest. You know, if this constant, density of the gas will increase with pressure. When pressure increases, density will increase. Density will increase when temperature reduces. Therefore, this should be at what? High pressure and low temperature. At these conditions, the gas has highest density. So which one is then give this one? High pressure and low temperature. You know, this condition can be satisfied in the second answer. Here STP means standard temperature and pressure, 0 Celsius and 1 atm. But in second answer it's 0 Celsius and 2 atm. High pressure is good for this one. So second one is the correct answer. Question number 6 again from quantum numbers. The energy of an electron in an atomic orbital of multi-electron atom. Multi-electron atom means the atom has more than one electron. It's not something like hydrogen, because you know hydrogen atom has only one electron. So if you get hydrogen as one electron, remember the energy varies according to the main energy levels only. That means if it is hydrogen, single electron 1, first energy level has this much energy, second energy level has this much energy. So this means 2s 2p, you know, second energy level has two main energy levels. This means energy of 2s and 2p are equal for atom like hydrogen, because it has only one electron, there is no electron-electron repulsion. But if it is multi-electron atom, you get more than one electron. That means there is repulsion. There is repulsion between electron. If there are some repulsions, then these type of sub-energy level then split. Then they split like this. So n equals 1, you have this much energy. But n equals 2, these split into two parts. 2s has low energy, 2p has high energy. This is for some atom like hydrogen containing single electron. but this is for some atom containing multi-electrons. Multi-electron. This is single electron one. So multi-electron species mean we get repulsion between electron. Only if you get repulsions between electron, sub-energy level then split according to these rules actually. S is lower than P. P is lower than D, like that. So then here you can see now energy of the electron here varies according to principal quantum number only, because it's just main energy level. But when you go to multi-electron atom, the energy varies according to principal quantum number. Other than that, according to azimuthal quantum number. You know, principal quantum number is okay 1, then here 2, right? But in this particular case, azimuthal quantum number or angular momentum quantum number for 2s is 0. This one is 1. So angular momentum quantum number varies, then energy also varies. That means energy depends on angular momentum quantum number. But once you go to magnetic quantum number, does energy depend on magnetic quantum number? I take this one, L equals 1. If L equals 1, you know, we can have 3 magnetic quantum numbers like -1, 0, +1. What magnetic quantum number gives us, it's about the orbital. In 2p, we have 3p orbitals. One can have -1, the ml. One can have 0, the other can have +1 or just 1. So here this can be then 2px, this can be 2py, this can be 2pz. These are the p orbitals that can be found in p sub-energy level. So what can you say about the energies of these 3p orbitals? Are they different? No, those are same. So then energy of that electron does not depend on the magnetic quantum number, and it doesn't depend on the spin quantum number also. So if you get electron up or down, it doesn't matter, we get the same energy. According to that, energy of an electron, that's a question. The energy of an electron in atomic orbital of a multi-electron atom depends on principal quantum number and azimuthal quantum number only. According to that, your answer should be second one. Question number 7, several oxides given, the correct order of acid strength. Maybe you remember we learned that one in P block. These are the elements you are given: aluminium, silicon, you know, aluminium here, silicon here, phosphorus here, sulfur here. Then the oxide formed by aluminium, it's a L2O3, silicon, it's a SiO2, phosphorus, it's given P2O5, sulfur, it's given SO3. These are the oxides we have. You know what happened to electronegativity going from here to here? Electronegativity increases. I'm talking about electronegativity of the element. Electronegativity increases. When electronegativity increases, acidity of oxide also increases. Acidity of oxide also increases. That's the point. So according to this, what should be the variation? This is how we get the variation. That's the correct order of acidity of this oxide. The reason for that is electronegativity. That answer is given in second answer. Question number 8, it's mixture of gases, two gases, methane and ethylene, exploded with 30 milliliter of oxygen, but oxygen is given excess. After cooling, the volume was 21 milliliter. Further treatment with caustic potash reduced the volume to 7. The amount of methane and ethylene in the mixture respectively. The answer is given in volume. So this means they are asked to find out volume of this gas mixture with respect to each gas. 10 milliliter of mixture of methane, methane CH4, it's a gas. Ethylene C2H4, it's a gas. Total volume of this gas mixture given 10 milliliter. I here ignore the unit, we know it's milliliter. This is exploded in oxygen. You know what happened if CH4 exploded in oxygen? We get carbon dioxide gas, and if it is high temperature, water should be gaseous state. But it says after cooling means low temperature. At low temperature then water should be in liquid state. But it's not balanced, we have to balance it. 1 carbon, 1 balance, 4 hydrogen, this should be 2. 2, 2, it's 4 oxygen, this should be 4. This is again exploded in oxygen, we get the same product, carbon dioxide gas and H2O liquid. First we have to balance 2 carbon here, 2 hydrogen, 4 hydrogen total. It's 2 water, 2, 2, 4, 2, 6, it should be 3 O2. But you are given now the volume of oxygen used. What is it? 30 milliliter, but it is excess. So what's the meaning of this excess? These two gases completely burn. Some oxygen will remain at the end. That's the meaning of this. But other than this, there will be another gas in the final gas mixture. It's carbon dioxide. Volume of this final gas mixture given 21. So what does 21 contain now? 21 milliliter contains volume of O2 remaining, volume of carbon dioxide 4. We pass this gas mixture through caustic potash. Caustic potash means potassium hydroxide, basic solution. Once you pass these two gases through basic solution, acidic gas dissolve. That dissolves in KOH. What is remaining gas? Remaining gas is here oxygen remaining. But the volume reduced to 7 milliliter. You know what happened from 21 to 7? Volume reduces. That's because carbon dioxide here absorbed by potassium hydroxide. Then you can say volume of carbon dioxide is 21 minus 7. It's 14. Total volume of carbon dioxide form, it's 14 milliliter. That's what we found. Then what about the volume of O2 remaining? It's 7. It's 7. So then we can find out the volume of CH4 like this. I assume volume of CH4 is V. Then ethylene, the volume will be 10 minus V. Total is 10. According to the stoichiometry, we get 1:1 here. That means 1 mole of CH4 produce 1 mole of carbon dioxide. V volume of CH4 should produce V volume of carbon dioxide. This is according to Avogadro's law. In Avogadro's law, volume is directly proportional to number of moles at same temperature and pressure. That means stoichiometry gives reactant mole ratio. It can be considered as reactant volume ratio. Here 1 volume gives 2 volume of carbon dioxide, then 10 minus V should give 2 times of 10 minus V. That's the volume of carbon dioxide formed. But do you know the volume of carbon dioxide? Yes, it's 14. From that you can find out finally the volume V actually. You can write it something like this. Volume of carbon dioxide formed in the first reaction plus volume of carbon dioxide formed in the second reaction is equal to the total volume of carbon dioxide. V plus 20 minus 2V equals 40. V plus minus 2V, it's minus V. We take that to the other side, take 14 to this side, 20 minus 14. So V equals now 6. If V equals 6, 10 minus V will be 4. So volume of CH4 should be 6 milliliter. Volume of ethylene should be 4 milliliter. Do we have that answer in the given answers? Yes, fifth one is correct. But I should mention this one. There is another possible answer for this question according to the given data. 7 oxygen remain. We used 30. Then what will be the reactant? Reactant will be this actually. 30 minus 7. It will be 23. 23 volume, 23 milliliter of oxygen reacted. If I consider these two now, one react with 2, then we react with 2V. One react with 3, then this react with 3 times. So this is reactant volume of O2. This is reactant volume of O2. Total volume of O2 reacted is addition of these two. That's equal to 23. One can take it something like that. So 2V plus 3 times 10 minus V equals 23. So according to that, 2V plus 30 minus 3V equals 23. 2V minus 3V, it's a minus V to this side, it's V. 30, we take 23 to this side, it becomes what? 7. V equals 7, then 10 minus V will be 3. So 7 and 3 is another possible answer according to the given data, right? So then CH4 volume can be 7 milliliter, C2H4 volume can be 3 milliliter. That's another possible answer according to the given data. Do we have 7 and 3? Yes, it's there in fourth answer. Therefore, there are two answers in the question, 4 and 5. Question number 9, hybridization involves. You know what hybridization? Definition for hybridization is mixing up different atomic orbital of same atom to form new set of orbital is called hybridization. In that case, mainly there should be different atomic orbitals of same atom, and then we get a new set of orbital. Mixing of atomic orbital centered on the same atom. Yeah, that's the correct answer. Mixing of atomic orbital centered on the different atom. So what is that called? You know, in the case of carbon, you remember that we get 1s2, 2s2, 2p2. In the ground state, we get the configuration like this. But one of these excited to this, we end up with excited state like this. If it is sp3 hybridization, this s orbital mix with 3p orbitals to form new set of hybrid orbitals. That process is called hybridization. That means S is from carbon, P also from carbon, same atom. Different atomic orbitals of same atom. But in the formation of CH bond, let's say this CH bond, sp3 hybrid orbital of carbon linearly overlap with s orbital of hydrogen. You see, sp3 orbital from carbon, s orbital from hydrogen. So if orbital from different atom combine mix, that is called what? Overlapping, not the hybridization. Mixing up these two orbital, hybridization. Mixing up these two orbital, overlapping. Addition of an electron to an atom, it's not a hybridization. Addition of electron pair to an atom, no. All are correct, no. So first one is the most appropriate answer for this. We are in now 10th question, but in 10th question there is missing part in the question, so you can have all for that. The root mean square speed of, that is the missing part, it should be of hydrogen. The root mean square speed of hydrogen gas is root 7 times the root mean square speed of nitrogen. If T is the temperature of the gas, then we have to compare the temperature of hydrogen and temperature of nitrogen. But it's about root mean square speed. You know the equation for root mean square speed? Root mean square speed is this. Root mean square speed. Root mean square speed is equal to square root 3RT over capital M. That's the equation for the root mean square speed. This is again a derived equation. You have to remember that one. If I apply this one to hydrogen, here it says root mean square speed of this root 7 times the root mean square speed of nitrogen. Okay, then let's take this one. X is the root mean square speed of hydrogen. That's equal 3R. Here T should be for hydrogen divided by capital M. So what's capital M? It's molar mass. Molar mass of hydrogen is 2. Normally the molar mass should be here kept in kilograms per mole. Then 2 10 to the power of minus 3 kilograms per mole. That's first equation. Then to nitrogen, then I take root mean square speed of nitrogen as Y. Then when you substitute the values 3R, this is temperature of nitrogen gas divided by the molar mass. Since it's N2, it should be 28 into 10 to the power of minus 3 kilograms per mole. This is second equation. We keep here kilograms per mole, that's to cancel some units. Now I divide first one by the second one. It's x divided by y. Root mean square speed of hydrogen divided by root mean square speed of nitrogen. You know, this can be something like 3r T of hydrogen divided by 2 10 to the power of minus 3. I ignore units, it's cancelled out. Multiplied by, what do we get? This is upside down. 28 10 to the power of minus 3 divided by 3r T nitrogen. That's what we have. Here 3r cancelled out. 3r cancelled out. 10 to the power of minus 3 cancelled. This is cancelled, it's 14. 28 divided by 2, 14. Then what do we get here? X divided by y. Root mean square speed of hydrogen is root 7 times this. That means this gives root 7 equals root 14 TH2 divided by TN2. That's the expression we have. But we can square both sides, so we get 7 equals 14 TH2 divided by TN2. But 7 14, you know, it's cancelled, it's 2 here. So what about then TN2? TN2 equals 2 times TH2. Right. So for this condition, temperature of nitrogen should be 2 times the temperature of hydrogen. That means temperature of nitrogen greater than hydrogen. Nitrogen is greater than hydrogen. So according to that, third one. Since hydrogen is missing in the question, you can have all. But once you look at the answers, you can predict it. You can guess it. The other gas is hydrogen. Okay, we are in 11th question. Orthonitrophenol. This O stands for ortho. More volatile than paranitrophenol due to, that's the reason. Orthonitrophenol. Phenol is this. You know that. Orthonitrophenol. These two positions are identified as ortho position. If it is labeled as number 1, this is number 2. Here, this is number 2. These two are ortho. Then we get nitro groups on ortho position. That's called orthonitrophenol. Orthonitrophenol. And this is phenol. These two position ortho, these two position meta, and this position is para. This is paranitrophenol. Paranitrophenol. Now we are going to find out which one is more volatile, but in this case it says orthonitrophenol is more volatile than paranitrophenol. Why? Volatile mean, you know, if you consider a liquid substance, we have particles like this. Volatiles mean liquid turns to gas. Liquids turns to gas. In the case of gas, we know interparticle distance is large compared to liquid. Therefore, converting liquid into gas means simply separating particles. Separating particles. But if the attraction between two particles is quite strong, if the two particles are strongly bound in the liquid, it is easy to volatile or difficult to volatile? If the particles are strongly attracted, it is difficult to volatile, right? So then in this case it says orthonitrophenol is more volatile. That means the interparticle attraction, that means attraction between two particles, two orthonitrophenols, should be weaker than the attraction between two paranitроphenols. That's the point here. But how can we understand it? If you carefully look at this OH group, you can see it's polarized like plus minus, delta plus, delta minus. This NO bond again polarized like this. Since there is two oppositely charged poles, plus minus, there can be new attraction between these two. I think you can identify that bond as a hydrogen bond. Why? This hydrogen is found in between two oxygen atoms. So it's hydrogen bond. But this hydrogen bond is found within the molecule, Therefore, this type of hydrogen bond is known as intramolecular hydrogen bond. Intramolecular hydrogen bond. So, if the molecule has intramolecular hydrogen bond, then ability to form intermolecular hydrogen bond is minimized. Why? Because already OH group attached to NO2 group present in the same molecule. If you consider another orthonitrophenol, there is no chance to attack that OH group to the other NO2 molecule, that OH group to the other OH group. Why? It's already attached to, bonded with this NO2 group in the same molecule. Therefore, in that particular case, intermolecular hydrogen bonding is minimized. But what happened to the para-1? Do we have a chance to make intramolecular hydrogen bond in para-nitrophenol? No. Why is that? These two are far away. OH and NO2 groups are then far away. Since the long distance is there, they can't make intramolecular hydrogen bond. Now OH group is now free. It's available for the intermolecular hydrogen bonding. So when you consider another para-nitrophenol, we can understand it. This is how we get OH group. This is how we get NO2 group. It's okay. In this particular case, this can be polarized like this. This can be polarized like this according to electronegativities. Now you can see there is chance to form hydrogen bond. But in that case, it's in between two molecules. So that's called what? Hydrogen bond, but intermolecular hydrogen bond. This is called intermolecular hydrogen bond. Right. Then which one has strong attraction between particles? It is here. Para-nitrophenol, there is hydrogen bond between two molecules. But I told you there is no chance, the chance is minimized for the intermolecular hydrogen bond between two orthonitrophenols. Because of that, here we have then strong attraction between particles. If someone has a strong attraction between particles, it's difficult to vaporize. Because of that, this is less volatile compared to this one. It's because of attraction. Intermolecular hydrogen bonding in orthonitrophenol and intramolecular hydrogen bonding in orthonitrophenol and intermolecular hydrogen bonding para-nitrophenol. That's the first answer. So that's the correct one actually. Here intra, here inter. That's the reason for this. Several compounds given in 12th question. You have to find out the thermal stabilities. We know going from left to right in a period, thermal stability decreases. Thermal stability decreases. Going down the group, thermal stability increases. That's what you learn in S block, inorganic chemistry. The reason for that one, here thermal stability increases. The reason for that one is mainly the polarization power of cation. That's the theory. The one which has higher polarization power of cation is thermally unstable. Because if the polarization power of cation is high, the deformation of electron cloud of anion easily. So when there is deformation of electron cloud in the anion, easy to break down. That means it undergoes decomposition. When it undergoes decomposition, it's thermally unstable. You learned that one in theory classes. Just remember this one. Thermal stability here increases because polarization power of cation decreases. So why polarization power of cation decreases? Because polarization power of cation depend on charge and the size of cation. When the charge increases, polarization power of cation increases. When the size decreases, polarization power of cation increases. When you go down the group, charge remains constant. It's not the predominant factor. But what happened to size? When going down the group, size increases. When size increases, polarization power decreases. Polarization power of cation decreases. When polarization power of cation decreases, thermal stability increases because ability to deform the electron cloud of anion here decreases. Then the bond is not easily broken down in the anion. Therefore, it doesn't undergo decomposition easily. That means thermal stability increases. But when you go from here to here, you know, polarization power of cation increases. Polarization power of cation increases. Again, you can understand why here the charge increases. When you go from group 1 to group 2, charge increases. What about the size? Size decreases. Because of these two factors, polarization power of cation increases, then thermal stability decreases because it easily breaks. Right, that's the point here. Then you can place down these things. Potassium carbonate, where you find potassium? It's here. Group 1. Lithium, sodium, potassium carbonate. Thereafter magnesium, lithium, sodium, then magnesium carbonate, group 2, it's here. Third period. Next, calcium, beryllium, magnesium, calcium here. Same group. Beryllium, it's here. Okay. How do we get this now? You know, going from here to here, group 1 to group 2, it decreases thermal stability. Going down the group, it increases. Then you get group 1 at the bottom and group 2 at the bottom. Then from here to here, it decreases. Therefore, potassium carbonate should have the highest thermal stability. Here the numbers. First one has the highest. Thereafter, calcium carbonate. Where you find calcium carbonate? It's third one. Next one, magnesium carbonate. It's in second place. Beryllium carbonate finally, fourth one. So this should be the variation. Then 4 to 1. 4, 2, 3, 1. That's given in second answer. So 13th question. There is an equation for the polymerization of ethene. Bond dissociation of CC double bond and CC single bond is given. The enthalpy of polymerization per mole of ethylene. To answer this question, you need some idea about the mechanism in the case of polymerization. Then only we can answer that question. And the other thing is, there is a mistake in the question about the data. If you just use 590, 330, you don't get the answer for this question. I mean, the answer is not given here. Actually, in this particular case, 330 should be 331. Bond dissociation of carbon-carbon single bond, it's given as 330, but it should be 331. So change it, 335. So you can have all for this again because of this data problem. But I will explain how to get the answer for this. During the polymerization of ethene, polythene is formed. This is the equation for this. But here I clearly show the bonds. You see, these are the bonds in ethene. But in times of ethene, N is an integer. It can be 10, 15, 100. That polymerized to give the polymer polythene. Here, I write the bonds like this. And this is represented like this. This means this unit repeated n times in the polymer. That's the meaning of this. Our question is to find out not the enthalpy change for this particular reaction. Okay, it's not delta H for this reaction. Why? Because delta H for this reaction, that means n number of polymers, ethylene, n moles of ethylene. But the question is per mole of ethylene. Per mole of ethylene. Per mole means if this is n, how to convert this enthalpy change for 1 mole of ethylene? Only thing you have to divide this one by simple ln. As example, if it is 2 mole, let's say 2 mole. For 2 mole we get 100 kilojoule. Then for 1 mole, it should be 100 divided by 2. Same thing. For n moles we get delta H. For 1 mole it should be delta H divided by simple n. That's the final answer. Final answer should be this. But first of all, let's try to find out delta H. Normally, according to the equation you learn in theory classes, enthalpy change of the reaction can be determined by using the bond dissociation enthalpies. Here's summation of bond dissociation of reactants minus summation of bond dissociation of product. That's the equation we have, reactant minus product. But we normally multiply this by the number of moles of bonds we have. We put it like MnN. Here the reactant, what is the reactant in this particular equation? It's ethylene. What are the type of bonds we break? We break CH bond. Delta H theta DCH, that's bond dissociation of CH. Let's forget about the standard condition. Is it given standard condition? Yes, standard condition given. Okay, we consider it. Delta H theta DCH, but how many moles of CH? 1, 2, 3, 4. There are in. So therefore it should be 4N. 4N times this plus other bond we break down is double bond. Delta H theta D CC double bond. But it's not just one, it's N moles in. That's reactant. Then we go to product. In the case of product, we again break CH bonds. Bond dissociation, CH bond. How many moles? 1, 2, 3, 4. Again, I told you this unit repeated N times. Therefore, it should be N times delta H theta D CH. That's what we have. Plus, there is one more bond. It's about CC single bond. This is where you need the mechanism of polymerization. Why? Here actually it's not just one CC bond. It's 2 CC bond. One unit, one monomer will produce 2 CC single bonds. Because during the mechanism, this is what happened. One double bond like this, another ethene molecule like this, right? This will deform the electron cloud of this unit. Then this electron cloud goes to the other side like this. This carbon takes positive charge. To neutralize this positive charge, this pi electron come in between these two, making new bond. Here again, there is another unit here. Then this make bond, new CC bond. If you carefully look at this, you will see what is remaining finally. C single, 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 single. But these two single bonds are formed as new bonds. So therefore, one monomer forms 2 CC single bonds. Can you see that? One monomer forms 2 CC single bonds. So that's why I just represent another CC bond here. Therefore, this is the difficult part actually. Most of you cannot then notice this part. We break 2N times D CC single bond. This is CC single bond. CC single bond 2 times. There are 2 but N, then 2N times. So that's the equation. So once we write this equation, then it will be easy to get it. You know, 4N DCH, 4N DCH cancelled out. In this case, yeah, it should be 1, 2, 3, 4. 4N DCH. That's cancelled out. What's remaining here? N times DCC bond. The value for DCC double bond, it's given 590 minus 2N times the value DCH given, CC single bond given 330, but I asked you to change it to 331. That's in kilojoules. So what we get? 590N minus 662 N kilojoules. So what is that? 2 minus 0, 2, 6 minus 9, it's 7, 5 minus 5, 0. We get minus 72 N kilojoule. Minus 72 N kilojoule. But you know, it's not the final answer, because to get this is per N moles. Per 1 mole, we have to divide that value by N. N means this number of moles. So then minus 72 N kilojoules divided by N moles. So N simply cancelled out. We get final answer minus 72 kilojoules per mole. That's the final answer for this question. So then there is one correction here. 330 should be 331. Therefore, you can get all for this. But I think you understood this procedure. Question number 14 from chemical bonding. The electron pair geometry and the molecular shape of XeOF2 respectively. XeOF2. Fluorine single bond because it's valency 1. Oxygen double bond because it's valency 2. Xenon from group 18, there are 8 electrons, 1, 2, 3, 4 involved in bonding. There will be 4 more. First question is to get the electron pair geometry. Yes, electron pair geometry can be predicted according to VSCPR. How many? 1, 2, 3, 4, 5 VSCPR. You know, VSCPR means simply sigma plus lone pair. Sigma plus lone pair. We ignore the pi bonds here. In this particular case, 1, 2, 3, 4, 5 VSCPR. Then you can predict the geometry. Geometry according to VSCPR. If it is 2 linear, 3 trigonal planar, 4 tetrahedral, 5 trigonal bipyramid. That's the geometry of this molecule. Next, we have to find out the shape. But shape is predicted according to bonding pairs and lone pair, you know. Here 3 bonding pairs are there and 2 lone pairs are there. 3 and 2. What's 3 and 2? T shape. This is T shape. So trigonal bipyramid and T. Trigonal bipyramid and T. Oh, yes, it's fifth. Fifth answer. 15th one, 3 gases of densities given. Densities are different here, but the volume is same. Pick up the correct statement. This is your system. Volume of this sample is given 4 liter capacity. 3 gases are there. Those are A, B, C. These are the gases given. Gas A will tend to lie at the bottom. That's wrong. Why? When you get gas mixture, remember, it forms a homogeneous mixture. It's a homogeneous one. It doesn't matter gas A is heavy, gas B is light, gas C is again heavy. No. If you have a gas mixture, remember, it forms a homogeneous mixture. Homogeneous means we can find A everywhere in the system in same composition, B everywhere in the system, C everywhere in the system, but they have same composition. Same composition is found in each place here. Therefore, it's a homogeneous one. We can't say gas A will tend to lie at the bottom. No, that's wrong. Number of atoms of various gases A, B, C are same. You know, we can't predict it like that. First thing, number of moles should be same. Then we get same number of molecules. But only if the molecule has same number of atoms, we get same number of atoms in the final. We get same number of atoms. But we don't see those information. I mean, we don't know molar mass of these gases to find out moles. We don't know the molecular formula of these to find out number of atoms. So therefore, it's not correct. We can't say it's same. Third one, the gas will diffuse to form homogeneous. Yes, third one is correct. Average kinetic energy of each gas is same. Of course. Why? Definitely, the temperature of the sample is something like T. Gas A at T, gas B is at T, gas C also at T. Kinetic energy of gases directly proportional to absolute temperature. Actually, it depends only on the temperature. So, if the temperature remains constant, then kinetic energy of all 3 gases should be same. So, the fourth one correct. 3 and 4. Third one and fourth one. It's given in third answer. Yeah, third answer is correct. Question number 16. What is not true about hybridization? In the previous question, we discussed something about hybridization. Simply hybridization, mixing atomic orbital, different atomic orbital of same atom. Hybrid orbitals form relatively stronger bonds than pure atomic orbital. The question is not true. That's the question, right? Hybrid orbital form relatively stronger bonds than pure atomic orbital? Yes. The reason for that one is overlapping area of hybrid orbital are quite large. As example, let's say it's sp3 hybrid orbitals overlap to form bond. Then compare that with pp atomic orbitals. These are pure atomic orbitals, these are hybrid orbitals. But in the case of hybrid orbitals, this overlapping area is large compared to pure atomic orbitals. When the overlapping area is large, then that means they are bonded strongly. Strong bonds are there. That's true then. Hybrid orbital form sigma bond, of course. Linear overlapping, the result is sigma bond. Orientation of hybrid orbital depend upon the type of hybridization? Yes. If it is sp, it's linear, only 2 hybrid orbitals. sp2, there are 3 hybrid orbitals, then trigonal planar. sp3, there are 4 hybrid orbitals, then tetrahedral. That's true. Promotion of an electron from lower subenergy level to higher subenergy level of the valence shell is essential for hybridization. That's not true. We don't need always the excitations. We need excitation to make some vacant orbital. If the vacant orbitals are available, then no need to promote electron from the low energy level to high energy level. As example, hybridization of nitrogen in NH3. In that case, in NH3 nitrogen atom already 3 unpaired p orbitals electrons are there. Right. So then to make 3 more NH bonds, we need 3 more unpaired electrons. So it's already available. Because of that, excitation is not important in that case. So therefore, that's the false statement. It's the answer for question number 16. Size of sp2 larger than sp. Of course, when you get sp hybrid orbital like this, sp2 can be something like this. When p character increases, size increases. sp3 can be like this. P character increases, size of hybrid orbital increases. Therefore, that's again true. Fourth one is the answer. Question number 17 from energetic unit 5. Enthalpies are given. Accordingly, what is the standard enthalpy of formation of CS2? That's the question. I start with combustion of CS2. That's the equation for the combustion of CS2, but enthalpy change for this one is given minus 1110 kilojoules per mole. That's the enthalpy change for the combustion. If you consider this reaction, this equation, enthalpy change of the reaction is given by standard enthalpy change of formation of product minus summation of standard enthalpy change of formation of reactant. But we multiply this by the stoichiometric coefficient. That's the equation to find out the enthalpy change of a reaction if you know the formation enthalpies. But here standard enthalpy change of the reaction is known. It's minus 1110 kilojoules per mole. That's equal to product, formation of product. What are the product we have? We get carbon dioxide, 1 mole. Formation of carbon dioxide is given in the first equation. It's for 1 mole, 395 into 1 plus sulfur dioxide formation, but it's 2 moles. Sulfur dioxide formation given in the second equation. For 1 mole, it's minus 295. It should be multiplied by 2 because it's there are 2 moles of SO2. That's minus the reaction, formation of reactants. So reactants we get CS2 and O2. You know O2 is an element. Then standard enthalpy change of formation of an element is equal to 0. So you can just ignore that oxygen part. Go to CS2. That is the question. Delta H theta F CS2 is the question. Now you can subject this one. Delta H theta formation of CS2. That's a question. You can take it out here. And then you can take that part to this. Then 1110. This becomes plus now. And this will be minus. Minus, minus. It will be minus. 395. Minus. 2, 5, it's 10. 18, 19. 509. It's kilojoules per mole. So what do we get now? It's 5, 9, 9, 18, 1, 8, it's 9. 5, 2, it's plus, yeah. Plus 125 kilojoules per mole. It's given in the fifth answer. Question number 18. Which among the following metal gives 5 different products on reaction with nitric acid depending upon the concentration of nitric? You know, nitric is oxidizing agent. Therefore, it undergoes reduction. Sometimes it reduces up to the stage of hydrogen. Sometimes it reduces up to the stage of ammonia. Sometimes it reduces up to the stage of nitrous oxide. Sometimes it reduces up to the stage of NO, nitric oxide. Sometimes it reduces up to the stage of NO2. So we have several stages of reduction of nitric. But this depends on the concentration of nitric, temperature of the reaction, and the nature of the other metal we have. According to these factors, sometime it reduces to this, sometime here, sometime here. So we get different products. In this particular case, hydrogen can be given. Nitric reduce up to hydrogen only with two metals. Remember that one. It's with magnesium and manganese. Only magnesium and manganese react with very diluted nitric to produce hydrogen gas. It's 1 to 2% of nitric. It's only magnesium. Therefore, remember, if magnesium is there, it can react with a very diluted nitric. That means 1 to 2% nitric to produce hydrogen gas. Magnesium with cold dilute nitric. This is cold dilute nitric. It can reduce this nitric up to ammonium. We have total ammonium nitrate, complete compound. It reduces up to ammonium -3. Magnesium with nitric, but hot diluted nitric. With hot diluted nitric, this can give nitrous oxide. It can give nitrous oxide with hot diluted nitric. But magnesium with concentrated nitric. This is concentrated nitric. This will be reduced up to nitrogen dioxide. In all these cases, magnesium nitrate is formed. Now we can see they give different product, 5 different product. 1, 2, 3, 4, 5. We can have 5 different products here. We get water also in these type of cases, right? So, but we have 5 different products. But other metals will not produce hydrogen easily. So therefore, other metals will not give 5 different products according to the concentration of nitric. So therefore, most appropriate answer for this question should be magnesium. It is better to maintain your note during this discussion because you learn these concepts in theory classes in different places. But in the question, we take concepts from several places and then organize to answer the question. So therefore, it's a different note then. I think it is highly effective before you go to the examination, just to refer and have a good idea about the subject. This note will be very helpful. So it's then good, it's necessary, I think, to prepare a note, a kind of review during this paper discussion in your word, right? So when you are close to the examination, very close to the examination, then you can go through that note and then have all the important points you need to know to answer your A-level paper, right? So because of that, I don't give time to prepare the note. I don't then give the note. I want you to prepare your note yourself in your words. Let's move to question number 19. This is from again inorganic. An aqueous solution of a gas X. X is a gas treated with hydrogen peroxide. Gas X, this is a gas. Aqueous means this dissolves in water. We get the solution. Aqueous solution of gas X treated with hydrogen peroxide. This is treated with hydrogen peroxide. We get the resultant solution. Let's say again solution. Okay. And thereafter allowed to react with barium chloride. This is treated with now barium chloride. We get a white precipitate insoluble in nitric. We get white precipitate. This is insoluble in nitric. Insoluble in nitric. That's the point. Now you are asked to find out the gas X. 5 answers given. If I go with these 5 answers, H2S, if it is H2S gas, with water it gives H2S aqueous. H2S aqueous with hydrogen peroxide will produce sulfur precipitate. Understand? So H2S aqueous with hydrogen peroxide, you can have sulfur precipitate. Why? This can act as oxidizing agent, hydrogen peroxide. Then -2 can be oxidized to 0. But in this case, it says solution. It's not solution, there is a precipitate. And that solution should react with barium chloride to form white precipitate. But you know, sulfur will not react with barium chloride to form white precipitate. Therefore, it's not the hydrogen sulfide. Next, carbon monoxide. Carbon monoxide plus water, let's say carbon monoxide aqueous plus hydrogen peroxide. Yes. In this case, hydrogen peroxide can oxidize this to carbon dioxide. This can go to, in the primary stage, this goes to hydroxyl, but hydroxyl will react, oxidize carbon monoxide to carbon dioxide. Other product is here hydrogen. That's how it react, oxidize. Anyway, carbon dioxide is formed. Then solution is carbonate actually. So if you get carbon monoxide aqueous plus water, carbon dioxide, but since water is present, this can be carbonate ion. Carbonate ion. Then barium chloride. Do we get white precipitate here? Yes, carbonate react with barium chloride to produce barium carbonate. It's a white precipitate. Is it soluble in nitric? Yes, carbonate, barium carbonate soluble in nitric because they react and give carbon dioxide, barium nitrate. Because of that it dissolves, but this says insoluble. It's not the answer. Next, sulfur dioxide gas. Sulfur dioxide gas with water, sulfur dioxide aqueous. Oh, we have sulfite. We have this as sulfite ion. SO4, SO3 2 minus. This is with hydrogen peroxide. You know, sulfite will oxidize to sulfate ion. Then sulfate ion can give white precipitate with barium chloride. It is barium sulfate. It's barium sulfate white precipitate. So is this soluble in nitric? No. Barium sulfite soluble, but not barium sulfate. Then your answer should be sulfur dioxide. When you go to the other carbon dioxide, we have the same thing, carbon dioxide, hydrogen peroxide, we get again carbonate. There is no oxidation reduction here. But carbonate with barium chloride will produce barium carbonate white precipitate soluble in nitric, not the answer. Nitrogen dioxide. Nitrogen dioxide, okay, can be oxidized to nitrate, but barium nitrate is not a precipitate. There is no precipitate in the case of nitrogen dioxide. So our answer is then third one, sulfur dioxide. We are in 20th question. When a substance A react with water, it produces combustible gas B. A react with water, B, it's a gas, I put it like this, but this is combustible. Combustible means you can burn that gas easily. Solution of a substance C in water. C is a solution. When another substance D react with this solution C, it also produces the same gas B. Okay, this solution treated with D substance, we get same gas B, that combustible gas B. On warming, but D can produce B on reaction with dilute sulfuric acid at room temperature. This D can react with dilute sulfuric H2SO4 to produce again B. That means this D react with both C solution and sulfuric to produce same gas B. A imparts deep golden yellow color to smokeless, right? A give golden color, golden yellow. We carry out the flame test here, flame test. So it gives golden yellow. This gives very clear idea about the cation in A. Definitely the cation should be sodium. So A is sodium. When sodium reacts with water, you know sodium is highly reactive metal. It reacts with water producing sodium hydroxide. This C should be sodium hydroxide and gas is hydrogen. Is it combustible? Yes, it's combustible. Hydrogen can be burned. Then you know this D substance reacts with base to produce hydrogen. D reacts with acid to produce hydrogen. D, you know now hydrogen, it's hydrogen. This is hydrogen. D reacts with base to produce hydrogen. D reacts with acid to produce hydrogen. Then what can you say about D? It reacts with both acid and base. Then D should be an amphoteric metal. Okay, then this is found in fifth answer. Fifth answer is the correct one. Fifth one, sodium, A sodium, right? B hydrogen, right? C sodium hydroxide, right? D given zinc. You know zinc can react with sodium hydroxide. Zinc, sodium hydroxide. Sodium zincate, you can say Na2 is the NOH 4 times plus hydrogen gas. Zinc plus sulfuric, you can say zinc sulfate plus hydrogen. With dilute sulfuric, this is how we get hydrogen gas. So correct answer should be 5. Okay, last 5 questions. Those are ABCD type question. You know how to answer. Instructions are given. In this case, then we have to go to each and every statement and see whether the statement is true or false. What is correct about sulfur? P block, inorganic. Monoclinic and rhombic sulfur has S8 form. Yes, we know rhombic and monoclinic, they have crystalline form and S8 molecule. That's true statement. Enthalpies of formation of these are different and delta S theta values are 0. You know, formation of sulfur rhombic 1 mole should be from thermodynamically most stable allotropic form. It is again rhombic. Since both sides are same, delta H should be 0, delta S should be 0. Formation of rhombic, enthalpy change 0, enthalpy change 0. But when you go to monoclinic, 1 mole of monoclinic is formed from thermodynamically the most stable allotropic form. That's rhombic. Then when rhombic goes to monoclinic, can enthalpy change be 0? No, it's not 0. Can entropy change be 0? No, it's not 0. Therefore, that statement is false. This says enthalpy of formation of these are different. It's okay. These are different. One is 0, the other is not 0. But delta S values are 0? No. It's false then. Standard enthalpy of transition of monoclinic sulfur is an extensive property. We have two type of properties, intensive properties and extensive properties. Intensive property means the property which does not depend on the mass. Extensive means which depends on mass. This is statement given standard enthalpy of transition. When we say standard enthalpy of transition of monoclinic sulfur, you know, standard enthalpy change of transition of monoclinic means one monoclinic goes to other allotropic form, let's say strombin. But this says standard transition enthalpy. When I say standard, here I refer 1 mole. I refer 1 mole here, right? So as example, standard enthalpy change of formation of water is minus 286 kilojoules per mole, right? So then it doesn't depend on the mass of water, right? So if you get 2 kilogram of water and 10 kilogram of water, in both case standard enthalpy change of water is minus 286 kilojoules per mole. It remains constant, right? So that means when I say standard, it refers 1 mole, therefore it doesn't depend on the mass of the substance we have. Doesn't depend mean it's intensive property, but this is a statement given, it's extensive property, therefore it is false statement. Okay, intensive mean independent, does not depend on mass. Some example, temperature, density, hardness, refractive index, those properties are intensive property. Extensive mean depends on the mass, volume, those are extensive properties. Okay, then A correct, B wrong, C wrong, D correct. So D, delta G theta 0 only for rhombic sulfur and monoclinic sulfur has value. Yes, in this particular case, you know, delta G also 0, but here delta G is not equal to 0 for the formation. So therefore that statement is true. A and D correct mean fourth answer. You are given a reaction in the case of 22nd question. It's this 3OH react with sulfur 3S, given sulfide plus sulfide and hydrogen, H plus ion. When you carefully look at the oxidation numbers, this oxygen minus 2, this hydrogen plus 1, this sulfur 0, elemental form. But this sulfur, you know, plus 4, this oxygen minus 2, this sulfur minus 2, this hydrogen plus 1. That's how we get the oxidation numbers. Then no change on oxygen, no change on hydrogen, but sulfur oxidizes. Again sulfur reduces. So what is this? This is an example for disproportionation reaction. Sulfur oxidize, sulfur reduce. Sulfur is an oxidizing agent? Yes, because it reduces. Sulfur is a reducing agent? Yes, because it oxidizes. OH minus oxidizing agent? No. OH minus reducing? No. There is no change on OH minus. So A correct, B correct. That's the answer. Question is the correct statement. A and B, first one. 23rd question, the concentration of an oxalic acid solution should be determined through a titration. Oxalic acid through a titration. So this is where you have oxalic acid H2C2O4. Then we should add something to this, and that should react with this. It's X or something. If you are to determine the concentration of this through titration, in the case of titration, there should be a vigorous reaction between these two. That's a main requirement. Vigorous reaction should be there. Then you have to find out which of these compound can react with H2C2O4 vigorously. First one, potassium permanganate. Can it? Potassium permanganate, you know, it can reduce easily to Mn2 plus if it is acidic medium. Basic medium MnO2. It reduces anyway. You can see plus 7 goes to plus 2. Can oxalic oxidizes? Of course, in oxalic we get C2O4 minus, then it oxidizes to carbon dioxide, carbon plus 3, this plus 4. Then can permanganate react with oxalic? Yes, it's possible. Sodium hydroxide, is it possible? Can X be sodium hydroxide? You know, if it is sodium hydroxide, there can be reaction with oxalic acid. There can be acid-base reaction. It's possible. In the case of titration, we have redox titration, we have acid-base titration also. Then if it reacts with here acid-base reaction, so it gives sodium oxalate and water. Then using an indicator, we can identify the endpoint. So therefore, X can be sodium hydroxide. It's possible. Sodium thiosulfate given. In the case of thiosulfate, S2O3 2 minus, it can go up to S4O6 2 minus. So what is this? It's 2 times and 2 electron. This is oxidation. It's oxidation. You know, oxalate, again we have oxidation. So can there be reaction between these two? No, there cannot be reaction. To oxidation, there is no reduction, no reaction. Potassium iodate, next one, iodate, IO3 minus. Potassium iodate, IO3 minus. IO3 minus can go to I2 easily. During this process, you can see plus 5. Is it plus 5? Yeah, plus 5 goes to 0. It's reduction. Depending on the medium here, it can sometimes go up to I minus. In that case, further reduce minus up to minus 1. So it reduces mean oxalate oxidizes. Yes, that can be used. So A, B, D. 3 answers correct. That means other responses 5. Solubility of lithium fluoride less than the solubility of other halides of group 1 element. The possible reason, this is about solubility of ionic compounds. We can understand the solubility of ionic compound in terms of hydration in enthalpy and lattice dissociation enthalpy. You remember that if hydration enthalpy is more than the lattice dissociation enthalpy, that ionic substance is soluble in water. This says lithium fluoride is less soluble. Lithium fluoride less soluble mean it should be something like other way around. It's less soluble mean lattice will be high, hydration will be low. In the case of lithium fluoride compared to the other halides of group 1. Let's take lithium fluoride, Li plus F minus. I take one more halide like sodium plus F minus. This is less soluble. Less soluble, this is more soluble. Which one then explain this phenomena? I told you less soluble mean this should be other way around. I mean lattice should be large. It's correct because lithium plus is small ion compared to sodium plus. Small ion mean here lattice energy will be large. Understand? So lattice energy inversely proportional to the size of cation. Size decreases, positive charge density increases, then plus minus ions are strongly bound, then lattice enthalpy increases. That's the point. Since lithium plus is small compared to sodium plus, this has high positive charge density, strong attraction, then high lattice energy. Then high lattice energy mean, increase in lattice energy mean it becomes soluble or insoluble? Insoluble or less soluble. Why? Lattice should be small compared to hydration to be soluble. Lattice increases mean it becomes less soluble. Then that is one correct possible explanation. High dissolution enthalpy of lithium fluoride, small radii of lithium plus F minus. hydration enthalpies of lithium plus F minus, high lattice energy of lithium fluoride. Actually, in this case, high dissolution enthalpy of lithium fluoride, it can't be. Dissolution means lithium fluoride plus water gives lithium fluoride aqueous. This enthalpy change is dissolution. If it is high dissolution enthalpy, that means this reaction is favorable. Favorable means this is more soluble, but statement is less soluble. Therefore, it is not a correct reason for this. A is not the one. Small radii of lithium plus and F minus. F minus is common anyway for both case. Yes, small radius of lithium plus. Small radius means high lattice energy. That means less soluble. High lattice energy means solubility decreases. That means less soluble. Therefore, it can be a possible reason for this. B. C. High hydration enthalpy of lithium plus F minus. It can't be reason for this case. Less soluble. You know, hydration enthalpy increases mean this is greater than lattice, then it's more soluble. If hydration increases, the solubility should increase. But this says less soluble compared to other halide. Less soluble mean then hydration increases. No, it's not correct reason for this. It can't be accepted here. D. High lattice energy of lithium fluoride. Yes. Since small size lattice energy is high lattice energy mean less soluble. Solubility decreases. So therefore, here the response is 5 because B and D are possible reasons. B, D mean 5. We have come to last MCQ. The statement that are true for the long form of the periodic table. It reflects the sequence of filling the electrons in the order of sub-energy level S, P, D, F. First hydrogen, helium, so S. Then lithium, beryllium, boron, again still S. Carbon, nitrogen, then P. Then we get the potassium, again S. Calcium, S. Thereafter we get scandium, D. After D, again fill in P. So you can see then it doesn't reflect in that order S, P, D, F. It helps predict the stable valency states of the element. Yeah, we can say like that. As example, if it is group 1 element, valency is 1. Group 2 element, valency is 2. Group 13 element, valency is 3. Group 14 element, valency is 4 or 2. So to predict the valency, the position of element in a periodic table is important. It reflects trends in physical and chemical properties of element. Yeah, we can say like that because you know, some physical property like electronegativity increases along a period, down group it decreases. Then atomic radius decreases, increases. So likewise, to predict some properties, yes, we can say the periodic table is helpful. It helps predict the relative ionicity of the bond between two elements. Yes, you know, to be more ionic, in the case of metal and non-metal, to be more ionic, there should be large cation and you know, small anion. Large cation and small anion. In that case, according to the position of this in the periodic table, the sizes can be compared. You know, size decreases from left to right. Size increases from top to bottom. Therefore, to be more ionic, you know, it should be cation somewhere here, anion somewhere here. So therefore, according to the position of this in periodic table, you can compare the ionicity. So it's again true. So again 5, B, C, D, several answers. Okay, this is end of then discussion of MCQ paper part 1.